right, thank you. I appreciate your having me here. So the title of this talk is a pair of references, one biblical, one modern. The biblical reference is the parable of the wise and foolish builders. The wise man built his house upon the rock, the foolish man built his house upon the sand, and when the rains came tumbling down, the wise man's house stood, while the foolish man's house was swept away. I've been a vocal critic of the Ethereum project since its very beginning due to not only the lack of formal methods going into it, but also the outright scorn that its developers heaped on the very idea of needing some formal structure in their grand plan, right up until it became clear that their grand plan was vulnerable to the tune of tens, even hundreds of millions of dollars. The Ethereum Classic world has the opportunity to move its operations onto solid formal foundations, and a lot of this talk will be about not only what this involves, but why. The modern reference is to Philip K. Dick, who wrote The Man in the High Castle and the stories that became Minority Report and Blade Runner. It's from a talk he gave in 1978 called How to Build a Universe That Doesn't Fall Apart 2 Days Later. If you've heard the line, reality is that which, when you stop believing in it, doesn't go away, that's where it's from. The cryptocurrency world has been, not to put too fine a point on it, a kind of sketchy one since the very advent of Bitcoin. Where money goes, scammers will follow. From exchanges that disappeared overnight, taking thousands of people's coins with them, to the deceptive contract that took down the DAO and led to the birth of Ethereum Classic, cryptocurrencies have had to contend with an awful lot of beliefs that went away even while people kept trying to believe in them. Ethereum Classic has committed to not rewriting the history of its blockchain, and that's one way to create ground truth that doesn't go away. But thanks to the shit sandwich you inherited, there's still a lot of work to do before the ground beneath your feet is really stable enough to trust, and today we're going to talk about why that is. I don't expect that most of you are particularly security-oriented, so I'm going to start with an overview of language theoretic security, what we mean by it, and the reasons why it's particularly relevant to smart contracts. The rest of the talk will focus on formal verification, what that means, what it can do, what it can't do, and why it matters, as well as how it currently applies to Ethereum and what work remains to be done. We're also going to talk a lot about usability, particularly when it comes to the design of programming languages like Solidity. And we'll wrap up with some thoughts on what Ethereum Classic can do to really become a platform where code is law. But before we can answer the question, what is language theoretic security, we also have to be able to answer the question, what is language? Well, the human languages, or natural languages that you speak every day, or that I'm speaking to you right now, are made up of words, which are symbols that refer to certain meanings or semantic content. We compose these words into phrases, and even more semantic content emerges out of the structures of these phrases. We gain information about direction, or temporality, or comparative degree. Your semantic inventory, the set of concepts you know about, probably has references for things that are merely red, like a brick or an apple, and things that are very red, like a fire engine or a particularly bitchin' Camaro. The adverb phrase modifier in the adjective phrase points you, the listener, at which referent, which concept to retrieve. But of course, there's more to natural language than just words and phrases. Phrases compose into clauses, and this behavior is governed by rules in much the same way that there are rules that govern the way that words compose into phrases. Now add in rules for what kinds of clauses are valid sentences and which ones aren't, and how to compose clauses into sentences, and you end up with a syntax for generating statements in English. But it goes even farther than that. For a sentence to be valid, it has to actually mean something. The linguist Noam Chomsky has a classic example of a sentence whose syntax is legitimate, but whose meaning is total nonsense. Colorless green ideas sleep furiously. When we talk about the meaning of an expression, we're talking about semantics again. Furthermore, expressions often consist of more than just one sentence. You've been watching me stand here and express for several dozen sentences now, and the meaning embedded in the overall discourse of this talk consists not only of the semantics I express in each sentence, but the interplay between those ideas, comparisons, contrasts, building on previous ideas, and so on and so forth. When we talk about a conversation, or even just a monologue, we're talking about discourse. The last important characteristic of human language is pragmatics. Pragmatics has to do with the cues, whether textual or spoken, that occur in a discourse as a way of preserving and clarifying meaning. They're tools that people use to keep from being misunderstood, like emphasis, cadence, and tone of voice. If somebody's ever completely misunderstood you, not because of what you said, but because of how you said it, like introducing too many ideas too quickly, or pausing in the wrong place, or saying something in one tone of voice when they expected another, you've experienced a pragmatics failure. Common knowledge is another aspect of pragmatics. What you know that the other person knows that you know that they know that you know, and so on and so forth. And all of these properties of human languages carry over into programming languages, which makes sense, right? Humans created programming languages, after all. The job of a compiler or an interpreter is to turn source code into machine code or byte code. But the job of a programming language is to turn the ideas in a developer's head into source code that will produce the results the developer wants. So in programming languages, the smallest building blocks are called tokens. Tokens are also symbols, and those symbols also have certain meanings, like here's a variable, or add the left operand and the right operand of this symbol together. Tokens are the vocabulary of the language, and the rules for composing tokens into statements and expressions is called a grammar. The good news here is that programming language grammars are way simpler than natural language grammars, because when we do them right, we start with a formal definition of the tokens and the rules of the grammar. With natural language, if we want to understand the grammar, we have to try to recover the rules based on the output of possibly millions of different speakers, all of whom might speak subtly different dialects of their language. This is not supposed to happen in programming languages. Two compilers for the same language or two interpreters for the same language should always agree on which inputs are grammatical and which inputs are ungrammatical. But sometimes they do disagree, especially when the grammar of the language is designed on an ad hoc basis and encoded implicitly in a handwritten parser. Handwritten parsers also often don't know what to do when presented with input their developer didn't expect. For a parser to be correct, it also has to be complete, meaning it has to respond appropriately to all possible inputs, and most handwritten parsers don't. These problems give rise to an entire class of vulnerabilities, which we'll talk about shortly, but we've got more analogies to make before we get there. A sentence is the natural language unit of a complete thought. In programming languages, a complete thought is called a statement. Usually, one statement corresponds to one line of code, although it's often possible to combine or chain statements together into bigger statements. Of course, this also happens in natural languages. It's called a compound sentence. But in many programming languages, it's common to see many statements chained together like a giant run-on sentence. This can have implications both for usability and for our ability to reason about code, and so can scope. Scope has to do with where in your code you define the symbols that you create, like variables and function names and so on, and whether they can refer to each other. We typically refer to this as visibility. When there's a mismatch between what a developer thinks about scope, about what concepts have been introduced to the code and where, and the visibility relationships that actually exist in the code the developer wrote, this kind of misunderstanding can lead to catastrophic bugs, and in Ethereum it already has. Naturally, expressions in programming language also have semantics. They mean something, or they should anyway. Just like the formal grammars we can use to specify programming language syntax, we also have formal systems for specifying programming language semantics. Denotational semantics characterizes the meanings of expressions in terms of mathematical functions, and operational semantics characterizes the meanings of expressions in terms of logical propositions and proofs about them. But just like grammars, programming language semantics are often specified on an ad hoc basis, with the only official specification of the semantics being the reference implementation of the language itself. For mainline Ethereum, the CPP implementation is the official reference implementation, and the yellow paper, despite the fact that it's supposed to be a denotational semantics of the Ethereum virtual machine, plays second fiddle. The yellow paper was stapled on after the fact. If the two disagree, the C++ implementation takes precedence. Down that road lies madness. When two implementations don't agree on semantics, or when a developer misunderstands the semantics of the language they're using, bugs arise. If anything, this matters even more in programming languages than it does in natural languages, because programming languages have side effects and computers have neither agency nor morals. If I accidentally tell you, take $10,000 out of my savings account, you might do that if you're an asshole with no sense of decency and the credentials to my bank account. If I accidentally tell a smart contract, send 10,000 Ether from my account to your account, or suicide this entire wallet contract, that's it. There's no consideration, no remorse, and no backsies. A side effect is any change in the state of the world, and with smart contracts, nearly everything that matters is a side effect. So finally, the equivalent of pragmatics in programming languages is what we call style. Style has to do with the conventions, the social norms, if you will, that developers arrive at in their use of a language. Some languages enforce certain aspects of style in their syntax. For example, Python requires you to indent the bodies of functions, conditionals, loops, and so on. This is partially for the interpreter's benefit, the way that curly braces in Java or C tell the interpreter where a block begins and ends, but it's also for the benefit of developers. You can see, based on the indentations, which lines of the code are executed together, because the visual grouping of the lines of code corresponds to the logical grouping of expressions as the interpreter understands them. But most stylistic norms are more like gentlemen's agreements or even just advice. They're not necessarily the law, but they're often a good idea. The security considerations section of the Solidity documentation is an example of this kind of style guide. And when style is all that stands between you and the market capitalization of your cryptocurrency, you have bigger problems. So what I hope you're starting to see is that any kind of program, including a smart contract, requires a certain kind of mutual understanding between the programmer and the compiled or interpreted results of their code. If the program does more than the programmer expects, or does something other than what the programmer expects, the programmer may be in for a nasty surprise. Later on, we'll take a close look at how fallback methods have violated programmer expectations in extremely expensive ways. But before that, let's talk about what both the machine side and the human side of this symbiotic relationship are responsible for guaranteeing to each other. First and foremost, a program's inputs must be well-defined. Whatever the grammar of its input language is, it must be able to recognize inputs that are valid in the input language, process only them, and reject everything else. For decades now, the vast majority of software vulnerabilities have been input handling errors of one kind or another. An attacker carefully crafts an input that shouldn't have been accepted, often because some of the values in it are inconsistent with each other in some way that makes a difference to the internal logic of the program. And that internal logic dutifully does the inconsistent thing in a way that does something the attacker wants. Payload length fields, whose values are different from the actual length of the payload, are a common culprit here. We've seen these lead to everything from integer overflows to key material compromises. Heartbleed back in 2013 was an example of this kind of bug. Protocols have grammars too. There's code in OpenSSL that has to parse TLS messages, and when the part that parsed heartbeat packets encountered one that was ungrammatical in a particular way, it processed it anyway, and the result was behavior that the OpenSSL developers certainly never intended. I realize I'm hammering this point about grammatical correctness over and over again, but it really is that important because crafted inputs are just that good of a way to manipulate programs whose input handlers don't know how to say no. Most of the categories of vulnerabilities on the Open Web Application Security Project's top 10 list are input handling bugs of one kind or another. But over and above this, it's also important that two implementations of the same specification exhibit identical behavior. Each of them had better accept what the other one accepts and reject what the other one rejects. Otherwise, someone, somewhere, will come up with a way to leverage the discrepancy. In 2009, Dan Kaminsky and my late husband Len Sassaman and I did exactly this to forge SSL certificates in about a dozen different ways, and that was just messing with syntax. We came up with ungrammatical certificate signing requests that certificate authorities were lax enough to sign, and we used the resulting ungrammatical but signed certificates to fool browsers into thinking we had valid certificates for any site we wanted. But agreement on semantics is crucial as well, which is why formally specified semantics that you can generate an implementation from are so important. In the Ethereum case, the problem is even worse, because discrepancies between implementations can lead to consensus failures between clients, and in fact, this has already happened. These are the minimal standards that we have to expect from a system in order to be able to expect it to act predictably, which I assume we want in a system of contracts. But there are expectations that humans have to fulfill as well. First of all, the programmer has to understand themselves what it is they're trying to do. Garbage in, garbage out can happen at any stage of the pipeline, including between the keyboard and the chair. So it's also the programmer's job to decide what constitutes a valid input and what doesn't. If the programmer's idea of the input language is ill-defined or incomplete, that incompleteness will make its way into the input handling code, and the program won't know enough about the input language to be able to hold up its end of the bargain. Similarly, just as implementations have to agree on semantics in order to produce expected behavior between them, the programmer and the implementation had better agree on semantics as well. Where this gets tricky for humans is when programming languages exhibit implicit behaviors, effects that show up in the running code, but which aren't necessarily obvious from the source code. And the worst part is that all the responsibility is on us. If we want safe, reliable software, then we don't just have to live up to our end of the bargain. We have to rigorously check that the machines live up to their end of it. The goal of language theoretic security is to be able to do exactly that in a principled way. I realize that's a lot of concepts to take in all at once, so let's recap. On the one hand, formal methods give us the tools we need to make sure that code actually does what we want. If we define our input languages formally using a grammar, we can be sure that our code only operates on valid input. We can obtain the same kinds of assurances about protocol behavior by formally defining the state machines a protocol uses. If we have an executable semantics of the language we're using, then as long as we know what behavior we expect out of the code we've written, we can make assertions about that behavior and prove whether the code we wrote actually does what we expect it to. On the other hand, cognitive science presents us with guidelines for keeping the systems we build comprehensible. Programming languages, APIs, and protocol design all need to take human limitations into account. You may have heard of the magical number 7 plus or minus 2. This comes from the research of George Miller, a psychologist who studied working memory. It turns out that for an average person, the number of items they can think about at any given time is somewhere between 5 and 9. If the amount of state that a programming language demands its users reason about is larger than the amount of state that you can reasonably expect someone to be able to reason about, that language's users are going to have a bad time. Putting it all together, if you want code to be law, the meaning of that code must be unambiguous, and users must have the same understanding of it that machines do. And we don't have to fantasize about what it looks like when widely used code turns out not to work the way its developers thought it did, because we already live in that world. Heartbleed, shell shock, image tragic, stage fright, the CCS injection vulnerability, the Android master key bug, Ghost, HTTPoxy, every single one of these bugs stemmed from some piece of code treating some invalid piece of input like it was legitimate and processing it anyway. And you may be asking yourself, what's the track record of smart contracts like in comparison? I have bad news for you. So let's consider the history of Ethereum so far. Vitalik's white paper came out at the end of 2013, and Gavin Wood followed up with a denotational semantics in the yellow paper a few months later. There's a pre-release in May 2015, experimental release in July, followed by a stable release in March 2016, and then all hell breaks loose. I don't have to tell you about the DAO. It's why Ethereum Classic exists in the first place. 2017 has been a veritable hit parade of smart contract bugs. In January, the Hacker Gold token had to be completely reissued due to a typo that reversed 2 characters. In July, someone exploited a vulnerable interaction in the parity multisig wallet contract between a delegate call instruction and a fallback method to steal $31 million worth of Ether. And the only reason they didn't get away with another $150 million worth was that someone else noticed it happening, stole it all before the original attacker could, and gave it back to its original owners after the bug in the contract was fixed. At least in August, there was some good... Whoa. That was bad. So at least in August, there was some good news. And that was when the KEVM team released their operational semantics for the Ethereum virtual machine. We're going to be talking about KEVM quite a bit later on in the talk. So moving on, though, okay, so in October 2016, we see the Metropolis release of mainline Ethereum. And then in November 2017, we see yet another we see yet another parity multisig wallet attack, this time to the tune of $153 million. I mean, this is just kind of off the chain. So, I mean, in the original yellow paper, Gavin Wood claims that the reason for the gas mechanism is to, quote unquote, sidestep the inevitable issues stemming from Turing completeness. The problem with this is it doesn't actually work the way that he thinks it does. I mean, if you believe this, you're hiding your head in the sand. You simply cannot cheat Rice's theorem. What Rice's theorem says is that all properties that are true for so what Rice's theorem says is that all properties that are true for at least one possible program, but not for all possible programs, are about the semantic behavior of an arbitrary program are undecidable. There's no general way to evaluate these kinds of properties for all possible cases in a finite amount of time. Does this program run for more than 1,000 steps is in fact what they call a non-trivial property. Non-trivial here meaning that it's true for some programs but not all of them. It's completely decidable, but it's not a semantic property. It has nothing to do with meaning. You can prove that a contract will run out of gas eventually, but you can't prove that it won't do anything malicious before it does so. doesn't do anything malicious is a semantic property, a property about the meaning of the contract. The gas mechanism is trying to use a non-semantic property to get around a well-established theorem about semantic properties, and it turns out that doesn't work. Gas doesn't actually sidestep the problem. Instead, it creates an adversarial game out of tricking the gas mechanism. And of course, there's tremendous economic incentive to do this because the reward for tricking the gas mechanism is money. But it's actually even worse than that because the incentive to keep gas costs low motivates contract writers to leave out runtime sanity checks, evaluating a conditional cost gas. And if you don't know whether a particular sanity check is necessary, then you might just leave it out. It's easy to talk yourself out of it. And that's a beautifully perverse incentive because honest actors are slightly disincentivized towards securing their contracts, and the strongest incentive to analyze a contract's security properties comes from robbing people. I'm not the first person to point out perverse incentives in decentralized contracts either. I mean, when Dino Mark, Vlad Zamfir, and Emin Gunsir called for a moratorium on the DAO, they identified several perverse incentives in the DAO contract itself, and they were mostly ignored. Some perverse incentives are unavoidable once you've committed to a system. It would be pretty difficult to back out the gas mechanism at this point. It's so central to Ethereum. But if you're already stuck with one perverse incentive baked into Ethereum itself, it really behooves the contract developer community to get better at recognizing perverse incentives before baking them into their own designs. So, you may have heard of a competition called the Underhanded C contest. The C programming language is notorious for making its users do a lot of low-level state management, like allocating and freeing memory, checking bounds on arrays, and other fiddly things that higher-level languages abstract away from you. In the Underhanded C contest, your job is to implement some simple data processing task, like counting votes or processing an image, but in a way that also implements some deliberately malicious behavior, like miscounting votes or embedding hidden fingerprints in the processed images, without making the malicious behavior obvious. Right now, the smart contracts world is one giant underhanded contracts contest. Solidity in particular is a minefield of non-obvious behavior, which is a lesson the parity developers have learned twice now. I hate to keep busting on them because there are things that they're trying to do right, such as writing their client's implementation in Rust. Having a client written in a memory-safe language that's amenable to formal verification is head and shoulders above C++. But even a verified correct VM implementation can't save you from a contract that does something underhanded rather than what you think it should. The good news is that formal verification can help us to reason about contracts. So let's talk about how that works. As I said earlier, the yellow paper contains the semi-official denotational semantics of the Ethereum virtual machine. Semi-official because, again, if the yellow paper and CPP Ethereum ever disagree, the behavior of CPP Ethereum is the authoritative one. All the VM opcodes are defined as mathematical functions. This turns out to be a reasonably elegant way of expressing some often fairly complicated instruction behaviors. And since EVM opcodes are what Solidity compiles down to, those functions are what we want to reason about. Unfortunately, the semantics as they're expressed in the yellow paper aren't executable. And if we want to make computers reason about contracts for us, we need an executable semantics. In fairness, I don't actually know of any executable denotational semantics frameworks. But we do, however, have executable operational semantics frameworks. There's one from a different University of Illinois team called K, which is where the K in KEVM comes from. Operational semantics are a lot more algorithmic than denotational semantics. They step through the execution of the program. A framework like K lets you define the execution semantics in the forms of rules about the data types, and the opcodes, and the other units of meaning that you need to reason about in order to verify that your implementation is correct. Then you can automatically generate a verified interpreter directly from those rules. By verified, I mean it'll make sure that certain properties hold throughout execution, that integer overflows never happen, that EVM machine words use the right mod 256 semantics, that the VM state reverts to the right state when an exception happens. Essentially the same kinds of properties that the parity team will be verifying about their client when they get to that stage. And their effort is still worthwhile because Rust is fast and compiled, and unfortunately generated interpreters are pretty slow. The KEVM interpreter is about 20 times as slow as CPP Ethereum, which is actually not terrible considering that the only other executable Ethereum semantics out there is about 100 times as slow. Moreover, not only does the automatically generated interpreter pass all the compliance checks, when they ran a semantic coverage analysis over the test suite, like doing a code coverage analysis to make sure that your tests exercise all your code, except a semantic coverage analysis makes sure all the semantic rules are exercised, they found gaps in the test suite. It turns out that in the official VM test suite, there are no tests for invalid opcodes and none for delegate call. Take a minute to let that sink in. The opcode that was at the heart of the parity hack back in July has no VM test coverage. To this day, it still doesn't. There are blockchain tests and state tests that exercise it, sure, but in the VM tests themselves, there are no tests of delegate call. Again, this is malign neglect. What if you're only writing a VM and not the rest of the client, like, say, Sputnik? I checked, and Sputnik VM only runs the VM tests, which means that delegate call isn't actually covered under Sputnik's tests. This is actually also true for KEVM, although the authors say in their paper that in future work they'll also use the general state tests, and that's a start. But the real solution is to make the VM test suite complete. Sir Charles Anthony Richard Hoare, who invented, among other things, both software verification and quicksort, once wrote, "There are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies, and the other way is to make it so complicated that there are no obvious deficiencies." Your build instructions are part of your software design. Your test suites are part of your software design. Was it obvious that the VM test suite was deficient? Apparently not. I'll grant that a decentralized grid computer is pretty complicated, but that's still no excuse for leaving a non-obvious deficiency uncorrected once it was discovered. The Sputnik VM developers aren't wrong for thinking that a test suite labeled VM tests would exercise all the opcodes in the VM. Going by that label, that's a completely reasonable thing to think. But the label is false advertising. Think about it. Suppose you're developing an EVM implementation and you're using continuous integration like any reasonably modern software project. CPU time costs money, you run your test suites on every build, so you don't want to run suites that aren't relevant to what you're doing. A completely normal economic incentive to keep operating costs down, coupled with a test suite that leads you to believe it's complete when it's not, means you could ship code that's never been tested. Right now, somebody out there is thinking, sure, but wouldn't regular code coverage testing have caught that too? But the real power of formally verifying a VM goes way beyond demonstrating that you've tested all of it under some inputs. To explain why, though, we're going to have to talk about a thing called reachability. In computer science, reachability has to do with whether a system can get from one state to another. You describe those states in terms of things that have to be true in the start state, or preconditions, and things that have to be true in the end state, or postconditions. The really clever thing about doing this semantically is that you're verifying those claims not just for a handful of values, but for all possible values of the relevant types. If your code takes an integer and does something with it, the K-theorem prover can verify that the postconditions hold for all integers that satisfy the preconditions. In this way, reachability analysis allows you to prove certain safety and liveness properties of your code. If you want to prove that some particular bad thing doesn't ever happen, that's a safety property. And if you want to prove that some particular good thing does always happen eventually, that's a liveness property. The K-framework also ships with a semantic debugging tool. It can generate a debugger for any set of semantic rules in pretty much the same way that it can generate an interpreter. And the debugger behaves about like you'd expect a debugger to. You can step forward and back in the execution and introspect on the state at any given time. But instead of stepping by instructions like you'd do in GDB, you're stepping by evaluations of semantic rules. What's great about this is that it also helps you debug the reachability claims that you're making about your program by letting you see how the state changes from evaluation to evaluation and figure out what the preconditions and postconditions need to be. So let's see a snippet of what it looks like to verify some EVM code, at least from a very high level. Since we need some EVM code to verify in the first place, step one is to compile your source code into EVM bytecode. All the examples in the KEVM paper are in Solidity, but you could totally do this with Serpent or LLL or any other language that compiles to the EVM. So on the slide is an example from the KEVM paper of one single reachability claim. This is for a piece of Solidity code that takes a positive integer n as input and returns the sum of the integers from 1 to n. So there's a well-known identity in math that this sum is equal to n times n plus 1 all over 2, and you can see in the third line there that they're asserting that equality. Furthermore, the line right above that starts with PC and angle brackets asserts a claim about the program counter. It says that at the time that the summation starts, which is a precondition, the program counter will be at 35, and then when it's finished, which is a postcondition, the program counter will be at 53. And then below that, there's a claim about what the gas balance will be before and after this part of the execution. This all gets fed to the theorem prover along with the EVM bytecode itself, and the prover verifies whether your reachability claims are valid or not. So this is great because now we can have a lot more assurances that there won't be unexpected interactions in our code. But the downside to this is that not only do we have to think carefully about what interactions we do expect and make reachability claims about them, we also have to think carefully about what interactions we don't want to have happen. Formal verification doesn't get to cheat Rice's theorem either. We still can't make claims about non-trivial semantic properties on arbitrary programs, though we can make claims about non-trivial semantic properties on a specific program. The catch is that we have to tailor our claims to the program itself. There is no general solution here. And if you're going to prove a claim, you have to make it first. If you missed some subtle semantic nuance of the code that you wrote and you don't verify any claims about it because you didn't realize that nuance was there, an adversary can still exploit any vulnerability there. So let's move on to the cognitive science aspects of LANGSEC. This is the part where I pick apart what went wrong in all those vulns I mentioned earlier. And my argument is that it has everything to do with processing fluency. But before jumping straight into that, I'd like you to consider this excerpt from the book Engineering a Safer World by Nancy Leveson. This is basically the book on systems engineering for safety. And one of its most important lessons is that accidents usually don't result from just one component of a system failing. More often, what happens is that the way that two or more components of the system interact creates unsafe conditions, and the unsafe conditions are what lead to the entire system failing. In Phil Dian's analysis of the Dow exploit, he pointed out that this is probably why this exploit was missed in review so many times by so many different people. Reviewers tend to review functions one at a time and assume that calls to secure subroutines will operate securely and as intended. And like Tony Hoare observed, complexity can obscure deficiencies. It's crucial for developers to be able to process the interfaces they use fluently. So when we talk about processing fluency, we're talking about whether it's easy or difficult for people to process information in the way it's presented. A font that's difficult to read is an example of presentation that impairs processing fluency. Same goes for uninformative variable names. Writing is another kind of information processing. If a language is difficult to write, you can't perform that processing fluently. I'd even argue that in the case of programming, the error messages that you get back from the compiler impact processing fluency with respect to writing. If the error you get is uninformative, it's harder to figure out how to fix it. It's also important to be able to tell whether similar things are the same or not the same, and whether things are related in some way, and if so, how. In programming especially, being able to fluently understand control flow, the way that execution moves through the program based on the data that goes into it, is absolutely vital. Most importantly, though, if there are possible states of a program that the computer can get into, the programmer ought to be able to know about them. You can't reason about what you don't or can't know about. So I don't have to give this crowd any background on the Dow hack. It's the reason why we're here. The reason it happened is because of a phenomenon called recursion, which is what happens when a function calls itself or when two functions take turns calling each other over and over and over again. Now, recursion is incredibly useful, but it's also incredibly dangerous if misused. And mutual recursion in particular can be difficult to see in your code when it's happening, particularly when the functions that are calling each other are defined far apart from each other. Out of sight, out of mind. And this is much worse when it's possible for mutual recursion to occur between code that you wrote and code that somebody else wrote. In fact, Peter Vestines described exactly this in his article on Race to Empty, which preceded the Dow hack by a whole 9 days. He's talking about mutual recursion facilitated by attacker-controlled code. I mean, Slockett tried to claim on June 12th, 3 days after this post, that they'd found and fixed a recursive send-related vulnerability in one place in the code, but they didn't find all of them. It was premature confidence. Finding one bug manually does not mean that you found all of the bugs of that type in your code. It's easy to convince yourself that you're secure, but too many people don't realize this until complete system ownage is staring them in the face. I referenced Mark, Zamfir, and Searer's game theoretic analysis of the Dow earlier, but this line from it really stands out. They're speaking to the fact that unsafe behavior more often emerges from the interaction of several parts of a system than from a single system component failing, just like Nancy Leveson does. The Dow had defender-controlled parts and attacker-controlled parts, and an attacker figured out how to leverage a weakness in the defender-controlled part using code that they controlled. Moving on, let's look at the hacker gold reissuance bug. In this case, two characters being transposed turned an increment and assign operation, plus equals, into an assignment operation, equals plus. Even Vitalik admitted that the compiler should have caught this one. This is a different kind of processing fluency failure, about telling similar things apart. If the programmer couldn't see the typo, the compiler should have, and it should have alerted the developer about it. And I'd just like to point out here that Solidity's lexer and parser are both hand-rolled. It's a handwritten recursive descent parser. And although you can write these correctly and with good error handling, it's much more difficult to do so, and you often fail to catch nasty edge cases like this equals plus thing. There's a formal grammar of Solidity in the docs section. I don't have the slightest idea why they didn't use a parser generator like Bison, because Bison will emit parsers for you, in C or C++, and the warnings that it gives you about shift-reduce conflicts can help you catch weird errors like this one before they actually end up in your language. And failing that, a development environment that gave the developer incremental updates about the state changes produced by the code they're writing would have helped catch this much sooner. There's a fantastic talk by Brett Victor called Inventing on Principle that shows some examples of what that would look like, and I strongly encourage you to take a look at that. All right, so the parity multi-signature wallet has had a hell of a year. The hack that occurred back in July was another consequence of an unsafe condition created by the interaction between several components. In this case, our old friend, the fallback method, and the EVM delegate call instruction. If you caused the fallback function to be invoked on an initialized multi-sig wallet, and you didn't send any ether, but you did put a message in the payload, it would delegate that payload as a method call on the so-called wallet library. This is effectively a raw eval on the string in the payload. If you wouldn't do this in JavaScript, you shouldn't do it in Solidity either, but both languages sure do make it easy. Again, there was a perverse economic incentive at play. Executing a contract with a lot of logic in it costs a lot of gas, so they wrote a library contract to deploy just once and a much lighter multi-sig wallet contract that called out to it. It's a design pattern, but it turns out to be a spectacularly unsafe one. In this case, the attacker realized that if they could invoke the library's init wallet function on an existing multi-sig wallet, they could reinitialize it with themselves as the owner and then drain the wallet, which is exactly what happened, and exactly what the group that drained all of the rest of the affected wallets proactively had to do. In order to stop the bleeding, they had to bleed the patient out. Part of the problem here was that init wallet was a public method. Methods in Solidity default to public, which means that implicitly there's a whole lot more attack surface available that defenders have to reason about unless defenders are careful about method visibility. There was simply too much going on in the background for the parity wallet developers to see what was lurking. So the parity folks refactored their wallet code, and now an initialized wallet can't be reinitialized. This is good. But the library wallet had not had a init wallet called on it. I mean, it wouldn't have been the library anymore if that had happened. And, well, that's exactly what happened. Some jackass called a init wallet on the library, and lo and behold, it became a wallet. And then the attacker invoked the former library suicide method. And just like that, $155 million in ether is locked up in wallets that can't access the code that they need to be able to do anything at all. I mean, this is left pad all over again, but for multi-million-dollar table stakes. And I mean, I can sympathize with the drive to be economical, but at some point when a design pattern turns into a foot gun, it's really worth considering whether that design pattern is really worth still using. And I'm not trying to say that these languages are inherently evil or anything like that, but they do foster an awful lot of implicit behavior. And when you're playing for high table stakes and the attacker is able to control some of the code involved, implicit behavior is a recipe for disaster. If you aren't aware of it, you can't reason about it. And if you can't reason about it, you can't defend against it. Beyond that, evaluating raw strings as method calls from anyone and everyone is just a terrible idea. It's possible to make reachability claims about whether a control flow path exists between your start state and a fallback method supplied by an untrusted party, but given how baked into the language this particular language facility is, this is an invitation to unsafe interactions. So, is there any hope? Well, I hope I've convinced you how grave the lack of solid formal foundations throughout the Ethereum ecosystem is. And I hope I've convinced you not only that it's time to take action, but that action is indeed possible. I hope I've also given you a better idea of what developers are really doing when they implement a smart contract, and of why smart contract developers deserve languages and tools that help them to be better coders, not worse ones. There's actually a famous programming article called Worse is Better. It goes into extensive detail about why code that's more limited in functionality and doesn't necessarily do the right thing tends to get taken up faster than code that strives for simplicity, correctness, consistency, and completeness. What we found, though, in the security world is that sacrificing correctness and completeness in the name of being first to market creates a world of vulnerabilities with users as the victims. It is a plainly user-hostile way to go about developing software, and this is unconscionable in a financial system. This is a house built upon the sand. When your semantics are defined on an ad hoc basis, you are cursing users to trust that your code actually means what you intended. When your virtual machines are unverified, you're putting your users at risk of exploitable, incorrect, or undefined behavior. When your contract languages are unverified or unverifiable, you're placing users at the mercy of anyone motivated enough to reason their way into an edge case that exploits your contract, and there's a huge financial incentive to motivate them. When the program can do things that the programmer doesn't realize that the program can do, it's the users who end up with the unpleasant surprise. But it doesn't have to be this way. Instead of an ad hoc semantics, the Ethereum Classic community can standardize on a formal executable semantics. If it were up to me, I'd standardize on KEVM because it covers the entire semantics and the extracted interpreter is fast enough to be practical. Plus, it's going to get faster in subsequent work. If you go with KEVM as your specification, then you've already got a verified EVM, and you have a platform on which to build formally specified verifiable contract languages. And once you have those, you have the ability to build developer tools like IDEs and live debuggers and verification tools that help to reconcile any mismatches between what the program can do and what the programmer thinks the program can do. So you invited me here to talk about language theoretic security in Ethereum, and I'd be remiss if I didn't give you some actionable advice on how to move forward. I know I'm repeating myself, but I really can't say this often enough. Formal syntax and semantics is the very first step. You have one available in KEVM. You might as well use it. You also need to fix your test suites. If the official Ethereum test suite is deficient, then add new tests to address the deficiencies. As Ethereum and Ethereum Classic drift farther and farther apart over time, their test suites are going to do that as well, so you might as well accept that fact and finish them. You need languages that don't hide their behavior from you. Static typing is great, but it isn't enough. If you've ever programmed in Scala, you have some idea of just how much confusion implicit type conversions alone can cause. Implicit class behavior is insanity. You have some great programming language theory people in this community. Work with them. Build IDEs and tools that can make the invisible visible. Find ways to show people what a contract is really doing under the hood so that they can understand whether it's doing what they wanted or not. For bonus points, build an IDE in JetBrains MPS and give your users a projectional editor to work with. Let them edit the structure of a contract rather than having to fiddle around with JavaScript-y syntax. You need ways to see what's going on inside your program as it moves from one state to another. And you need that to be fluid and natural for users to work with. Again, Brett Victor's talks and essays have a lot of great material to mine here. And for the love of God, watch what the hell you're doing with naked evals in the form of delegate call. Now, the image on this slide, and also on my shirt, is due to Evie Namath, who was known as the godmother of Unix up until she was lost at sea a couple of years ago. Instead of the usual 7-layer OSI model of the network stack, it's a 9-layer model with financial above the application layer and political above that. You are here. You are in the layer that has to do with human decision making. Ethereum Classic stands at an important crossroads, and it has the ability to decide to build the most reliable, farthest reaching distributed system the world has ever seen. I hope my advice and suggestions have been useful. Again, thank you very much for your time. I'm open to any questions.